And welcome to today's lesson. In this first tutorial, we will be able to list and recognize the 6 sum or difference identities and be able to find the exact value using those sum and difference identities. So we are in section 6.4 in our textbook, Sum and Difference Identities. I'd first like to remind you that you should have your flashcards. We have 25 fundamental identities on our flashcards that we should be studying, and you should continue to study those on a daily basis. We're going to be adding 6 more in this tutorial, and we're going to be adding a few more throughout the rest of this chapter. Okay, so I'd like to ask you a question first. I'd like to know what you think about this. Does the cosine of 50 degrees equal to the cosine of 40 degrees plus the cosine of 10 degrees? Calculators are, of course, permissible if you'd like to plug that in the calc to see. I do know that the cosine of 50 degrees could be written as the cosine of 40 degrees plus 10 degrees quantity, sure. But the question is, I guess the question is, are we able to distribute a cosine symbol to each of these things and say that we can just take each of these individually and add them up? If you've already plugged it into your calculator, you know that that is a big fat no. This does not work. Unfortunately, that's just too easy and we can't have it that way. Trig symbols cannot distribute to a sum of two angles. That's why we actually have sum and difference identities. So when we're given two angles that are added up or two angles that are subtracted, we have an identity to deal with them. So this is absolutely not true. If you do have two angles added up, you need to use one of our sum or difference identities. Now, there are technically 6 of them, but I like to memorize them as 3 chunks. I see the sign of a sum, that's of course the plus sign, and I see the sign of a difference, and I actually memorize both of them together using a plus or minus symbol. Let me show you what this expands out to be. The sign of a sum, let's do the x plus y first, will equal the sine of x, the sine of the first angle, times the cosine of the second angle, and then you keep the same sign. So if you're talking about the sign of a sum, you're talking about a sum, and then it's the cosine of the first angle times the sine of the second angle. That's what the sign of a sum will be equal to. The sign of a difference is basically the same exact thing, except it's going to be a difference in between your two terms. So I just like to memorize it as two, or as one chunk. Plus or minus will stay plus or minus. The cosine, if we have the cosine of a sum, that's going to be equal to the cosine of the first angle times the cosine of the second angle, but then we change the sign to a minus sign, and then sine of the first angle times sine of the second angle. That's what the cosine of a sum is equal to. Notice that it has a minus sign. And then the cosine of a difference is basically the same exact thing, except this time it's a plus sign. So again, I can still memorize these two all together using a plus or minus on this side of the identity, but realizing with the cosine, I switch that to be a minus or plus symbol. So that basically the tops are the same. The plus sign here goes with the minus sign, and the minus sign here goes with the plus sign. And if you're trying to remember the difference between the sine and the cosine, some people might remember that the sine stays the same. And that might be just kind of a funny way to remember that. So if we're talking about the tangent of a sum, let's talk about x plus y, the sum. Well, the tangent is a quotient. It's usually the sine over the cosine. The tangent of a sum will be the tangent of the first plus the tangent of the second. That's what the numerator is. And then divided by 1 minus the tangent of the first times the tangent of the second. So that's what the tangent of a sum will be. It'll keep the plus sign in the numerator, but it'll be a minus sign in the denominator. Now if we talk about the tangent of a difference, again, it's basically the same exact thing, except this time it's a difference in the numerator, but a sum in the denominator. These are our 6 new identities for this section. Remember that the sign stays the same, but the cosine will change. And that's kind of helpful when you're talking about the tangent, because tangent is basically the sine divided by the cosine. So it makes sense that the sine, which normally would be up top, stays the same up top, plus or minus, plus or minus. But down here where the cosine would be, the cosine sign would change. So plus minus to minus plus. So I'm absolutely fine with your using only 3 flashcards to start to memorize these 6, or if you want to use 6 separate flashcards, that's fine. Just separate the plus and the minus onto 2 different flashcards. But now we have a total of 31 identities that we should have memorized. Now, we are sort of changing gears in terms of what we're doing with our identities. We're not going to be verifying identities like we've been doing the past few lessons. Now, these identities are, yes, of course, things that we need to memorize that are true, but really we're going to be using them. We're going to be applying them and basically using them, not memorizing them to necessarily substitute into other things. Let's look at our first couple examples here. It says to find the exact value. Now I know that the cosine of 75 degrees, that's not one of our special unit circle angles. So before, what we would have to do is plug this into the calculator, make sure we're in degree mode, and just give an estimate. But not this time. I want to know what is the exact value. And it's helpful because now I know the sum and difference identities. What I really need to do is look at 75 degrees and split that up into 2 of my special angles from the unit circle that either add to 75 degrees or subtract. And I think what most people tend to say is that the cosine of 75 degrees could be the cosine of 30 degrees plus 45 degrees as a quantity, because then I'm using 2 angles from the unit circle that I do know about. So we've got this, the cosine of 75 degrees. I can rewrite, there's actually infinite pairs that I could rewrite, but most people probably are going to do 30 and 45 or 45 and 30. Now, what I need to do now is understand this is a cosine of a sum, and I need to expand this into what that would be equal to. The cosine of a sum says that it's going to be equal to the cosine of the first angle times the cosine of the second angle, and then I change my sign, S-I-G-N, and then I've got sine of the first angle and sine of the second angle. That's from memory or from the previous part of the note sheet. So this is what we do. We expand into this. Now each of these quantities is something that I know. I know the cosine of 30 degrees from my unit circle, and I know this, and I know this, and I know this. I know all 4 of these values. Maybe what we should do is draw a picture of the unit circle just to remind ourselves. Let's do the cosine, let's do the 30 degrees. That's right here. I'll do that in blue. 30 degrees is right here. So if I'm talking about the cosine of 30 degrees, that's this long x distance, which is square root of 3 over 2. And if I'm talking about the cosine of 45 degrees, let's do that in a different color. Let's do that in purple. The cosine of 45 degrees, that's the one right in the middle, so it's the square root of 2 over 2. And then I've got my minus. And now let's go back and do the sine of 30 degrees. 30 degrees is right there. That's that little sign up 1/2. And then the sine of 45 degrees is the square root of 2 over 2. That was supposed to be a different color. So what I did was I took the 75 degrees that I don't know much about, split it up into 2 angles that I do know about for the unit circle, expanded using my identity, and then just replaced each of these things with the value from the unit circle that it is. Now I just have some multiplication to do. Square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. 1 times square root of 2 is square root of 2. 2 times 2 is 4. These two fractions want to be subtracted together, and it's a good thing since they have the same denominators that I can do that. Now the numerator, of course, becomes nothing that I can change. Square root of 6 minus square root of 2, they are not like terms, so I'll have to just write them side by side, but it's all over 4. There's the exact value of the cosine of 75 degrees. So let's look at part B. We have the sine of 7 pi over 12. Well, again, 7 pi over 12 is not one of the famous angles from our unit circle. So we're going to have to figure out what we can do to either add or subtract two angles that we do know that get 7 pi over 12. I'm going to actually keep it in terms of pi over 12 right now, and I'm going to say, well, I do know that 7 pi could be 4 pi plus 3 pi. So how about 4 pi over 12 plus 3 pi over 12? That's definitely true. The sine of this is still the sine of 7 pi over 12. And what that does for me is because 4 pi over 12 reduces to pi over 3, hey, that's one of our special angles. And 3 pi over 12 reduces to pi over 4. Hey, that's another one of our special angles. Now I've got it. Pi over 3 plus pi over 4 adds up to 7 pi over 12. So therefore, I can use the sign of a sum identity. And again, I can expand this out. Now I do need to remember what the sign of a sum would be equal to. So either go back and look at the identities at the top of our note sheet or do it from memory, but it's not probably there yet. Sine of the first angle times cosine of the second angle, keep the same sign, and then cosine of the first angle and sine of the second angle. Again, we need to expand using our identity. And again, the genius now behind this is that all 4 of these are representing special unit circle values. I just need to know what they are. I'm going to draw the unit circle again, or just a quick picture of it. Let's do with red. Let's do the pi over 3. There's pi over 3. So the sine of that is the long distance. So the sine of that is the square root of 3 over 2. The cosine, I'll come back to that. The sine over here, sine of pi over 4. Oh, sorry, I don't want to do that. I want to stick with pi over 3. The cosine of pi over 3, this time that's just the little x distance. That's 1/2. And pi over 4 is my other angle. I'll do that in fuchsia. That's the one in the middle. That means that the cosine and the sine are exactly the same distance. It's square root of 2 over 2. So that means that this is square root of 2 over 2. And this is square root of 2 over 2. So that's kind of helpful. I'll keep my plus right there. We can see that it's similar. It's a lot of the same numbers because there aren't that many different numbers in our unit circle. Here's my square root of 6 over 4, and here's my square root of 2 over 4. And I can combine those together. Again, you cannot combine the numerator terms because they are not like terms. So just write them side by side, and there's the exact value for the sine of 7 pi over 12. Let's look at a tough one, tangent. Tangent seems to be tough when we get into the later identities. Let's look at tangent of 15 degrees. The first thing I want to do is figure out how to rewrite 15 degrees as either the sum or difference of two angles that I do know. And you might be thinking about the 45 and the 30 again, but this time you'd be subtracting them, and that's good. I'm going to take the tangent of 15 degrees and rewrite it as the tangent of 45 degrees minus 30 degrees. That'll get me my 15. So now that I've found two angles from the unit circle that I can use, now I have the tangent of a difference. And I'd like to expand that out to be what that is equal to be. Okay, so the tangent of a difference, I've got to go look back at my identities. That's going to be the tangent of the first angle. Keep the same sign in the numerator, minus the tangent of the second angle divided by 1, and then change the sign plus, and then this time I'm going to multiply the tangent of the first angle times the tangent of the second angle. So that's what it expands to become. Again, I'm expanding using my identity. Let's see what angles we're talking about here. I'll draw my little unit circle again. 45 degrees, that's that one in the middle, and that's exactly how I remember the tangent. That's the 1 in the middle. So the tangent of 45 degrees turns into a 1. So I've got 1 and then minus, let's see, in a different color, 30 degrees, that's right here. 30 degrees is like a pi over 6. It's not like, it is a pi over 6. And since I see the 6, I remember that the tangent is going to be the square root of 3 over 3. It's the one with the two 3's. So I've got that divided by, let's see, I already have the 1 and the plus sign. There we go. And now those values repeat themselves again. Tangent of 45 degrees is 1, and multiplied by the tangent of 30 degrees, again, is square root of 3 over 3. Notice at this step, there's no more trig symbol. The tangent symbols are all gone, and we've replaced them with the values from the unit circle. There's no more trig. Now it's just some algebra, really. This time it's a complex fraction. We have a big fraction that has tiny fractions in it. What I'd like to do in this case is get rid of those tiny fractions, meaning I need to get rid of this denominator of a 3. So since it's really just a 3 I need to get rid of, I can multiply all parts of this fraction by 3. I can multiply this part by 3, this part by 3, this part by 3, this part by 3. I'm doing that with a 3 to get rid of these denominators. Let's see what this does for us. 3 times 1, of course, is 3, and then a minus. This 3 will cancel away. That's kind of the whole point, and I'm left with the square root of 3. So that's nice. And then I've got my fraction bar, the main fraction bar. 3 times 1 again is 3, and then a plus. This time, again, the 3's cancel away, and 1 times the square root of 3 would be left, and there we go. Simple way to get rid of a complex fraction is just multiply all parts by the denominator that you want to get rid of. Unfortunately, I'm not finished because I cannot leave a radical in the denominator. And this time, it's actually a binomial. And to get rid of a binomial, I need to undo that with another binomial. And hopefully you remember this from your algebra skills. If I'm trying to undo this binomial, I need to multiply by its conjugate, 3 minus the square root of 3, to the numerator and to the denominator. I might as well put parentheses everywhere now. Okay, to undo this and get this radical out of here, I need to multiply by the conjugate, which is basically just changing this middle sign, S-I-G-N. So let's see what we have here. I need to FOIL up top. 3 times 3 is 9. 3 times negative square root of 3 is negative 3 square roots of 3. And then another 3 times negative square root of 3 gives me another negative 3 square root of 3, giving me negative 6 square roots of 3. And then my last terms, negative square root of 3 times negative square root of 3 makes a positive 3. You might say, well, it's the square root of 9, and you'd be correct. Square root of 9 is 3. In the denominator, the whole point of multiplying by the conjugate is that the inner terms 3 square root of 3 and the outer terms negative 3 square root of 3 cancel away. So all I really need to do are the first terms, 3 times 3, and the last terms, positive square root of 3 times negative square root of 3 makes negative 3. Okay, it's getting better here. Let's clean up our like terms. I've got 9 and 3, that makes 12. I'll do it over here. 12 minus 6 square roots of 3. And in the denominator, of course, I've got 9 minus 3, which is 6. Oh, I'm so close. I see that all parts are divided, or I can divide everything by 6. So if I pull out a GCF up top of 6, I'm left with 2 minus the square root of 3. And then I can cancel that out as a common factor, and I have my final answer. Whew. Like I said, the tangents are a little bit more complicated when we get into the later stages of identities. But that's some good algebra work right past this point. Well, right past this point, really. Next. Part D. It's a little bit different. Looks like somebody actually already expanded this for us. Unfortunately, they chose some really weird angles. I don't know anything about 42 degrees or 12 degrees, so this expansion doesn't actually help me. What I want to do is condense it back Somebody just messed up and did some weird angles. So let's put together their stuff. The question is this a sine, is this a cosine, or is this a tangent? Well, of course it's not a tangent. So is it a sine or a cosine? We need to remember. And in this case, because it's a sine times a cosine, and then a cosine times a sine, I do remember that this is the sine. So it's the sine of, now it's going to be two angles, the 42 degrees and the 12 degrees, but the question is, are they supposed to be being added or subtracted? Well, since we know that it's the sine, we know the sine stays the same, so this must have been this. And 42 degrees minus 12 degrees is 30 degrees, and the sine of 30 degrees, we all know, is 1/2. You can look on the unit circle if you need to. So somebody took the sine of 30 degrees, for some reason changed it into 42 degrees minus 12 degrees and expanded it, trying to mess you up. But we're so good that we're able to take their expansion and condense it back to where it came from and tell me what the exact value is, which is 1/2. Okay, and this brings us to our final example. Example E, we're looking for the cosine of alpha plus beta. Unfortunately, we don't know what alpha and beta are. I know that we could figure out what they are, but actually it doesn't matter what they are. All we need to know is that it is the cosine of a sum, and we know what that's going to be equal to. Now, they do give us that the sine of alpha is 3/5, which doesn't really help us in terms of unit circle, because this is not one of our special unit circle values. And that gives us the cosine of beta is 12/13. Same dilemma. Doesn't really help us with the unit circle. But that's okay. Before we worry about this information, let's just expand what the cosine of a sum is supposed to be equal to. The cosine of alpha plus beta will be equal to the cosine of the first angle, alpha, times the cosine of the second angle, beta. Change the sign, and then the sine of the first angle, and the sine of the second angle. So there's our expansion. Expand it first. Now let's see what we need. Obviously, each one of these is going to be replaced by a certain value. Actually, we already know a couple of those values. We already know that the sine of alpha is 3/5. So where it says sine of alpha right here, I could put the 3/5. And we also know that the cosine of beta is 12/13. So where it says cosine of beta, I can put the 12/13. Unfortunately, that's all that I know. I'm missing the cosine of alpha, and I'm missing the sine of beta. And I'm not going to be able to find them from the unit circle. But that's okay. This is a triangle problem. In fact, it's a double triangle problem. I don't need to know what alpha is. I just need to be able to draw a picture of it. I'm going to draw a picture of alpha. And since it doesn't tell me what quadrant it's in, I'm just going to assume it's in the first quadrant. All I need to, here's a picture of alpha. I always make it look like a 45-degree angle, but that's just a picture. Here's my little right triangle. If I'm given the sine of alpha, that's like the SO of SOHCAHTOA. I know that the opposite is 3 and the hypotenuse is 5. So from where I'm standing, which is always the origin, the opposite side is 3 and the hypotenuse is 5. And now I know what this missing side is, because this is going to be a 3, 4, 5 right triangle. If you don't know what that missing side is, go ahead and use your Pythagorean theorem. But I like the 3, 4, 5, so there it is, 3, 4, 5. And now I can tell anything about this triangle, the secant, the cosine, the tangent, whatever I want. What do I need for alpha? I need the cosine of alpha. Now the cosine of alpha, which is ka, would be adjacent divided by hypotenuse, which would be 4/5. So now I'm missing sine of beta. That means I need to draw a beta triangle. Again, I'm just going to draw it in the first quadrant since it doesn't say otherwise. Here's my beta. Let's see what I've got. Cosine of beta, that's my ka. That means that the adjacent is 12 and the hypotenuse is 13. So here's my adjacent and here's my hypotenuse, which means that the missing side is over here, and now I know what it is because I know my Pythagorean triples, 5, 12, 13. If you have trouble figuring that out, again, use Pythagorean theorem. 13 squared, take away 12 squared is 25, and the square root of that is 5. So now what am I missing? I'm missing sine of beta. Now that I have a picture of beta with all three of the sides, sine of beta is opposite 5 divided by hypotenuse 13. So it's 5/13. So far I expanded using my identity and then replaced each of these values from a picture into these fractions. And now it's just some fraction work. 4 times 12 is 48. 5 times 13 is 65. There's a minus. 3 times 5 is 15. 5 times 13 again is 65. It's nice that the denominators will always be the same, so I can just simply subtract the numerators. 48 take away 15 is 33, and of course the denominator stays the same. This does not reduce, so I have found my answer. So if you don't have unit circle values, you can still draw pictures. That's, I think, the fastest way to do this. Thanks for watching this tutorial. We've got some practice to do, and please add these 6 identities into your flashcard bundle and continue studying all 31 of the identities at this point. I'll see you in class to practice. Bye-bye.